You know, I look at this table here, solid, steady, just sitting there. Looks perfectly still, nothing moving. You could swear it's at rest. Complete peace. And if I pick up this glass of water, same thing. Calm surface, no ripples right now. Everything seems quiet, motionless. But wait a minute, if you really think about it, if you imagine getting smaller and smaller, down past what your eye can see, down to the little bits everything's made of, those atoms, those tiny particles, they are not sitting still at all. They're jiggling all the time, bouncing around like crazy little kids in a playground that never closes, never stopping, perpetual motion. Even in this steel table, even in the coldest ice you can find, the atoms are vibrating, shaking, bumping into each other. Heat is just how fast they're jiggling. More jiggle means hotter, less means colder, but never zero jiggling, never complete rest, not even close to zero. Why is that? Why can't anything ever truly come to rest? Why does nature forbid perfect stillness? It's one of those things that seems so simple at first. Everything stops eventually, right? A ball bounces, slows down, rolls to a stop. We say it's at rest. But zoom in. The jiggling never quits. The atoms keep going forever, passing energy around, never quite settling into nothing. That's the puzzle I want to talk about tonight. That's the puzzle I want to talk about tonight. Because this endless motion isn't some accident. It's built into the rules of the universe. It tells us something deep about what things really are, about heat and energy, and why the world behaves the way it does. And once you see it, you can't unsee it. That still table isn't still at all. It's alive with invisible dance. You look at this table right in front of us, solid wood, heavy, it doesn't budge when you push it. It looks perfectly still, dead quiet, nothing happening. Same with a stone on the ground or a block of ice sitting in the freezer. We say that at rest. We talk about things coming to rest all the time. A ball rolls slower and slower until it stops. A swinging pendulum gradually quiets down. A cup of hot tea cools and settles. Everything seems to wind down to perfect stillness eventually. That's how the everyday world feels. But hold on. That's only how it looks from way up here with our big, clumsy eyes. If you could shrink yourself smaller and smaller past the wood fibers, past the molecules, down into the atoms themselves, you'd see something completely different. Those atoms aren't sitting still at all. They're moving, fast, jiggling, vibrating, bouncing into each other like a room full of excited kids who never get tired. Even in the hottest, coldest, most motionless piece of matter you can imagine, the atoms keep shaking. Take this table. At room temperature, each atom is vibrating back and forth around its average position maybe 1,000,000 times a second. The whole lattice of atoms in the wood is trembling. Atoms bumping neighbors, passing little kicks of energy back and forth. That trembling is what we call heat. Heat isn't some separate thing poured into objects. It's literally the random motion of the tiny pieces everything's made of. The hotter something is, the faster and wilder the jiggling gets. Cooler means slower jiggling. But here's the key. It never stops completely. You can cool things down a lot. Put something in liquid nitrogen down to minus 200 degrees Celsius. The atoms slow way down. Their vibrations get tiny. Go even colder into the millikelvin range with special refrigerators, and the motion becomes very feeble indeed. But no matter how hard you try, you never reach a point where every atom is perfectly motionless. There's always some leftover wiggle. Scientists have gotten within billions of a degree of absolute zero, but never quite to it. And even if you could get arbitrarily close, quantum mechanics steps in and says you still can't make the motion zero. Why not? Because at the smallest scales, particles are like little marbles you can pin down. They're fuzzy, wavy things governed by the uncertainty principle. If you try to force an atom or an electron into an exactly fixed position, perfect rest, zero momentum, the rules say its position becomes completely uncertain. It would spread out everywhere at once. You can't have both perfect stillness, zero momentum, and perfect location at the same time. Nature won't let you. So even in the ground state, the lowest possible energy of a system, there's a residual zero-point motion, a tiny unavoidable buzz that particles can't shake off. It's as if the universe has a built-in restlessness at the bottom. That means no piece of matter, no matter how cold, how isolated, how carefully you shield it from outside disturbances, ever truly comes to rest. The atoms keep vibrating with at least that quantum minimum. In solids, they rattle in place. In liquids, they slide past each other with constant motion. In gases, they're flying around at hundreds of meters per second, even when cold, even a single atom floating alone in empty space. If you somehow cooled it to its ground state, would still have that irreducible zero-point energy, making it restless. So what we call at rest is really just not moving much on human scales. Underneath, down where the real action is, everything is in perpetual motion. The table isn't still. It's alive with invisible dancing. The ice isn't quiet. It's trembling at the atomic level. This endless jiggle isn't a flaw or something we can engineer away. It's fundamental. It's the way the universe is wired. Nothing ever truly comes to rest, because perfect stillness would violate the deepest rule. Yes, we know both the thermodynamic rule that you can't reach absolute zero in a finite number of steps, and the quantum rule that forbids spinning everything down completely. The motion is always there, hiding just below what we can see, keeping the world from ever settling into true silence. That jiggling we see when we zoom in isn't just random bouncing. It's the very definition of heat. Temperature isn't some mysterious fluid or invisible substance added to things. It's a measure of how fast and how wildly those atoms and molecules are moving around. In a gas, the molecules fly through space, crashing into each other and the walls, changing direction every billionth of a second. In a liquid, they're sliding and tumbling over one another. In a solid, they're locked in a lattice, but still vibrating back and forth, rattling in their places like little springs that never quite settle. The hotter the object, the more violent the motion. Boil water to 1 Celsius, and the water molecules are leaping around with enough energy to break free into steam. Cool it down to room temperature and the jiggling slows. Freeze it into ice at 0 Celsius, and the molecules lock into a crystal pattern. But even then they're vibrating, less energetically but vibrating. Drop the temperature further, say to minus 200 degrees, with liquid nitrogen, and the vibrations get feebler still, the atoms barely twitching. Scientists have pushed this lower and lower with sophisticated cooling techniques, dilution refrigerators, laser cooling of atoms, magnetic traps reaching temperatures in a nanokelvin range, billions of a degree above absolute zero. But here's the stubborn fact. No matter how much you cool something, the motion never stops completely. You can get arbitrarily close to zero temperature, but you never quite reach it. The atoms always retain some tiny amount of kinetic energy. T. Hey, keep jiggling however faintly. This isn't because our cooling machines aren't good enough or because there's always a little heat leaking in from the outside world. Even if you could perfectly isolate an object in a perfect vacuum, shielded from every photon, every vibration, every stray particle, the motion would still be there. Why? Because perfect rest, absolute zero motion, would mean absolute zero temperature, and nature has a law that says you can't reach absolute zero in a finite number of steps. It's the third law of thermodynamics. As you try to remove the last tiny bits of heat, it gets harder and harder to pull more away. The entropy, the disorder approaches a minimum, but the process requires more and more effort for less and less gain. You can approach absolute zero asymptotically, getting closer forever, but you never arrive. Each cooling step removes less energy than the one before, and infinite steps would be needed to squeeze out every last joule of thermal motion. Even more fundamentally, quantum mechanics steps in and forbids it outright. At the very bottom, when you've removed almost all the thermal energy, you're left with the ground state of the system, the lowest possible energy configuration. But even in that ground state, particles aren't motionless. The Heisenberg uncertainty principle says you can't know both the position and the momentum of a particle with perfect precision at the same time. If you force the momentum to be exactly zero, true rest, the position becomes completely uncertain. The particle would be smeared out over all space, which is impossible for bound systems like atoms in a solid or electrons in an atom. To keep the particle localized in its proper place, its momentum must have some uncertainty, which means some minimum kinetic energy. This is called zero-point energy initial. This is called zero-point energy. It's the irreducible buzz that everything has, even at absolute zero. In a harmonic oscillator, like the vibration of an atom, in a crystal lattice, the lowest energy isn't zero. It's 1/2 h bar omega, half a quantum of vibrational energy. That tiny amount keeps the atom oscillating forever, never quite at rest, so the jiggling doesn't fade to nothing as temperature ups. It approaches a non-zero floor set by quantum rules. In helium, the lightest element, this zero-point motion is so strong that even at absolute zero, it refuses to freeze solid under normal pressure. It stays liquid because the atoms keep moving enough to prevent a rigid lattice from forming. That's liquid helium staying fluid down to the lowest temperatures we can reach. This means that on the deepest level, nothing ever truly comes to rest. What we call cold or still is always relative, less motion than before, but never zero. The universe doesn't allow a state of perfect quiescence. Rest is an illusion of scale. From far away, things look calm. Up close, in the realm where quantum rules dominate, everything is restless, vibrating with that fundamental, unavoidable energy that can never be taken away. The table, the ice, the single, trapped atom, they're all in perpetual motion, down where the real laws live. It's baked into the rules. The uncertainty principle says you can't pin down both position and momentum perfectly. So even at the lowest energy, particles keep a tiny restless buzz they can't shake off. Let's see how that works. Imagine you have a single atom trapped in some kind of little box, or better yet, vibrating in its place, inside a crystal lattice, like in the table we're looking at. Classically, if we pretend the world is made of little billiard balls, you could imagine cooling it until it sits exactly still at the bottom of its potential well, zero velocity, zero momentum, perfectly at rest. No more energy to take away. Done. But quantum mechanics. Physics doesn't let things behave like that. Particles aren't points with definite paths. They're described by wave functions, little probability clouds that spread out in space. The sharper you make that cloud, the more precisely you know where the particle is, the more the wave function wiggles in momentum space. That means the particle has a spread in possible momenta, some positive, some negative. The average might be zero, but the actual speed isn't zero. It's fluctuating around. Heisenberg's uncertainty principle puts a hard limit on how small both uncertainties can be at once. Delta x tracks stack path p create I tau, where I is Planck's constant divided by 2p pi. If you squeeze the position uncertainty delta x very small, say confining the atom tightly to its lattice site, then the momentum uncertainty delta p has to be at least h, 2 delta x. That minimum spread in momentum means a minimum spread in kinetic energy. Even when the average momentum is zero, the particle can't have exactly zero momentum. It has to jiggle back and forth with at least that minimum amount. This leftover motion is called zero-point energy. For something behaving like a harmonic oscillator, which many atomic vibrations do, the lowest possible energy isn't zero. It's 1/2 I omega, where omega is the natural frequency of the vibration. Half a quantum of energy forever. You can't drain it out. It's the ground state. The atom keeps oscillating with that amplitude, no matter how cold you make everything else. In real materials, there are many such oscillators, billions upon billions, even a tiny speck of stuff. Each mode has its own zero-point energy. Add them all up, and even at absolute zero temperature, the system has a huge total zero-point energy. But because it's the lowest state, you can't extract it to do work. It's stuck there, keeping things restless. This isn't just theory. We see it everywhere. In liquid helium-4, at temperatures below 1 Kelvin, ordinary thermal motion dies away almost completely, but the atoms still don't freeze into a solid under normal pressure. Why? Because the zero-point motion is so large. The helium atoms are very light, so the de Broglie wavelength is big and the uncertainty is strong. They keep sloshing around enough to prevent crystallization. You need to squeeze with 25 atmospheres of pressure to force solid helium at those temperatures. Without that pressure, zero-point energy keeps it liquid, perpetual quantum motion. In superconductors, electrons pair up and move without resistance, but even there, the underlying lattice vibrations, the phonons carry zero-point energy. In Bose-Einstein condensates, where atoms are cooled to nanokelvins and millions of them occupy the exact same ground state, you still have that residual quantum fluctuation. The condensate isn't perfectly still. It has quantum depletion, little bits of motion from the uncertainty. Even a single electron in an atom has zero-point motion. In the hydrogen atom, the ground state electron isn't sitting still at the nucleus. It's smeared out in a cloud with kinetic energy from that spread. Again, 1/2 Quamena kind of contribution in the effective potential. So at the bottom of the energy ladder, when you've removed every last drop of thermal energy, the particles don't stop. They can't. The uncertainty principle enforces a minimum kinetic energy, a built-in restlessness that no cooling, no isolation, no clever trick can eliminate. Perfect rest would require delta P equals 0 exactly, which would force delta X to infinity. The particle would delocalize completely, losing all structure. But real things are localized. They have definite places in crystals, in molecules, in traps. That localization demands momentum spread, demands motion. This quantum refusal to allow stillness ties right back to the thermodynamic side. The third, losses, entropy, approaches a constant, often 0 for perfect crystals, as temperature goes to 0, but it never quite reaches absolute 0 in finite steps. Part of why is this quantum floor. You can't cross that last barrier because the ground state itself isn't motionless. Everything we call at rest is therefore approximate. On macroscopic scales, yes, things look quiet, but down where the laws are written, in the quantum realm, nothing ever truly comes to rest. There's always that tiny eternal buzz, that unavoidable dance dictated by uncertainty. The universe doesn't permit perfect silence at the smallest scales. Rest is an illusion we create by not looking closely enough. The jiggling is fundamental, permanent, woven into the fabric of how particles must behave to exist as localized things at all. Nothing ever truly comes to rest, because perfect stillness would break quantum mechanics and thermodynamics at the same time. The universe is built to stay restless forever, down at the smallest scales. Put the two big reasons together and you see why rest is impossible. From thermodynamics, we learn you can't reach absolute 0 in any finite number of steps. Each time you try to pull away the last scraps of heat, it costs more effort for less result. The heat capacity drops, the entropy change per degree gets tiny, and you approach 0 temperature, like a curve that flattens out forever but never touches the axis. You can get to a millionth of a Kelvin, a billionth, even lower, with adiabatic demagnetization or laser cooling. But the process always leaves some residual thermal motion. The third law of thermodynamics isn't just an engineering limit. It's a statement that absolute 0 is unattainable because the system would have to cross an infinite series of states to remove every last bit of disorder and miss energy. In practice, no real process can do that. But even if thermodynamics allowed you to get arbitrarily close, if you could somehow magically remove all thermal energy, quantum mechanics still refuses to let motion stop. The uncertainty principle guarantees a floor. You can't have a particle with exactly 0 momentum while keeping it localized in space. Localization demands a spread in momentum, which means kinetic energy can be 0. For every bound system, atoms in a lattice, electrons in atoms, molecules in a gas, the ground state carries that irreducible 0-point energy. It's not a small correction or a side effect. It's the lowest the system can go. Take a harmonic oscillator, the simplest model for vibrations. Energy levels are n plus 1/2 xi omega, where n equals 0, 1, 2. The ground state has energy ha omega, not 0. Remove all thermal excitation. Set the average n to 0. And you're still left with that half quantum of perpetual oscillation. In real matter, this adds up in dramatic ways. In ordinary solids, at room temperature, the 0-point energy is tiny compared to thermal energy. So we don't notice it, the thermal jiggling dominates. But cool things down, and the thermal part fades, while the 0-point part stays fixed. At absolute 0, the entire lattice would still vibrate with that quantum minimum. The atoms don't sit motionless at their equilibrium positions. They oscillate around them with an amplitude set by the uncertainty. X-ray diffraction experiments at very low temperatures show this residual disorder. The Debye-Waller factor never reaches perfect sharpness because of zero-point motion. Liquid helium is the poster child for how strong this can be. Helium, 4 atoms are the lightest noble gas atoms, so the zero-point energy per particle is large relative to the weak van der Waals binding forces. Even when you remove all thermal energy below 1 Kelvin, the atoms keep enough quantum motion to resist forming a crystal lattice under normal pressure. They stay liquid, sloshing around in a superfluid state below 2.17 K, with zero viscosity because the whole system flows as one coherent quantum wave. Only when you apply about 25 atmospheres of pressure do you force the zero-point motion to yield and let a solid form. That's quantum restlessness winning over classical freezing. In ultra-cold atomic gases, Bose-Einstein condensates form when atoms pile into the ground state at nanokelvin temperatures. But even there, measurements show quantum depletion. A small fraction of atoms are kicked out of the condensate by interactions. Precisely because of the uncertainty-driven motion, the condensate isn't perfectly still. It has fluctuations that can't be eliminated. The same principle operates in every quantum system. In molecules, vibrational ground states have zero-point energy, keeping bonds from collapsing to zero length. In nuclei, nucleons have zero-point motion, preventing collapse. In quantum field theory, the vacuum itself bubbles with zero-point fluctuations, virtual particles popping in and out, because the fields can't have exactly zero everywhere without violating uncertainty. So perfect rest doesn't just require beating thermodynamics, it requires beating quantum mechanics too. You'd need to violate the uncertainty principle to pin momentum to exactly zero while keeping position definite. But if you did that, the particle would lose all localization. It would become a plane wave delocalized across the universe. Real localized objects, tables, rocks, atoms, you can't exist in that state. Localization demands momentum, uncertainty demands kinetic energy, demands motion. The universe therefore enforces perpetual restlessness at the fundamental level. What we perceive as stillness is always an average over huge numbers of particles or an approximation on large scales. Down where the rules are. Strict motion never quits. The table vibrates with thermal jiggle plus quantum zero-point buzz. The coldest trapped atom still oscillates in its ground state. No isolation chamber, no perfect cooling cycle, no theoretical trick can erase that last bit of dance. Rest is forbidden by the deepest laws we know. The cosmos is wired for eternal, subtle activity. Nothing, truly nothing, ever comes to complete rest. The jiggling continues forever, a quiet, unbreakable feature of reality itself. So there you have it, the table in front of you, the rock on the ground, the ice in the freezer, they all look perfectly still, but they are not. Down at the atomic level, everything is in constant motion, thermal jiggling that never quite dies out. And even when you strip away every last bit of heat, quantum mechanics insists on that tiny, unbreakable zero-point buzz. Perfect rest isn't just hard to achieve, it's forbidden by the laws of nature. Thermodynamics won't let you reach absolute zero in any real way, and the uncertainty principle won't let particles sit still, even if you did. The universe is built restless from the very bottom. Next time you see something at rest, smile a little. It's an illusion we live with every day, but the truth is wilder. Nothing ever truly comes to rest. Everything keeps dancing forever in that invisible quantum waltz. It's one of those beautiful, stubborn facts that makes the world feel alive, even when it looks quiet. Thanks for listening and thinking along with me. I hope this made you look twice at the still things around you.